This is the video that's going to finish up example 9 from section 2.6 day 3, finishing up that objective of analyze graphs of rational functions, and then we'll start on section 2.7 day 1. And first hour, I was running out of time, and I can't stand it when that happens, and then I tend to take shortcuts, and I didn't have my glasses on when I looked at where we were going to get this whole, and I missed the negative. So first hour, we take the x plus 4 out by canceling, and then put a negative 4 into what it would look like without that factor of x plus 4 in there. So we would have negative 4 times negative 4 minus 4, which would be negative 8. And then on the bottom we'd have 2 times negative 4 minus 1 is negative 5. 32 over negative 10, which would reduce to negative 16 fifths. So I just have to quit letting the clock determine, how worked up I get about these things, and then we'll be okay. So we've got all of these wonderful things just sitting here waiting for us to graph. And let's take a peek at that graph. And y sub 1 up there has my x cubed minus 16x, all divided by 2x squared plus 6x minus 8. And I'll do some zoom 6 here. Now, that looks more like what we think of when we think of hyperbolas. Two branches looking kind of symmetric, and what we have to do is think, okay, there's a lot of stuff I know about this, and there's pieces that I have to put on my graph. So we get down here to the graphing part, and we realize we put on that vertical asymptote yesterday, but we didn't get that slant asymptote on. And that slant asymptote is way back up here, and it's 1/2 x minus 3/2. So remember, slant asymptote, we don't need the remainder, we just need the quotient. So 1/2 x minus 3/2 would start down here at negative 1.5, and then we would go up 1 and over 2. And I'm going to do that several times. So I have a really nice drawing of my slant asymptote. All right, and let's label that one, because we always label our asymptotes so we can see what we have. 1/2 x minus 3/2. And we need some points that hopefully are on the graph. So go back and take a peek. We said we have an x-intercept at 0, 0, and that's our y-intercept as well. And then we have 4, 0, so 0, 0, and 4, 0. Seems to fit with what we have up there. All right, my sparkboard did some weird stuff there. So there are the points 0, 0, and 4, 0. And now has something to do with the blue marker. You got me. It doesn't like it today. We also had a hole, and that hole was at negative 4 and negative 16 fifths. So let's get that on before we do anything else. All right, so negative 4, negative 16 fifths would be negative 3 and 1/5. And we can see that's going to be pretty close in on that asymptote right there. But we'll need our table. And we need things that are going to be to the left of 1. Good numbers. We've got 0 already taken care of, so we'll try negative 1. We can aim at our hole, and then we'll try like negative 7 and negative 10. So we put that in, and that will give us a good look at our graph. So I'm going to go back and write these values down so that we can graph that. So -1 gives you -1.25, -7 is -4.813, and -10 is -6.364. Well, that's definitely going to close this in on that asymptote very, very close. So -1, -1.25, -7, and -4.813. And then at -10, -1, 2, 3, 4, 5, 6, just a little more, and it is super close to our asymptote. So I start graphing, making sure that I leave that nice little hole there. And then maybe we get a little nervous because we're like, well, we know from looking at the picture that, yeah, it's going to approach the asymptote, but what if I wanted to find 0.5? Well, remember, that's something that you can make your calculator do by going second window. I'll start it at 0, and I'll make it go by 0.5. Now, you could change it to 0.25, 0.1, whatever you want, but second graph gives you the table, and now we can see 0.5 is 1.75. Might not want to keep it that way forever, so make sure you change your window back. But that gives you something else to aim for, and every little piece of information that we have about this graph is important and significant because this is the first of the kind that we have seen here. So 0.5 was 1.75. But yeah, that definitely is hugging the asymptote very, very closely. Don't want that little bugger to cross it. Then we go over to the other side of 1. And some numbers over here, maybe 2, 3, and 10. That should give us enough to see what we need there. So 2 from the table is -2, 3 is -0.75, and 10 is 3.333. So 2, -2, 3, -3/4, and 10 is 3.333, which is going to come right up here into my table. Very, very close again to that asymptote that we have there. And away we go. Now, I have to remember that little hole. You know, that's really important, especially as we get down here to our domain. We've got our limits as we approach that asymptote of 1, and our graph is definitely going up forever, so infinity. And as we come down from the right in, let me draw on top of that right here, we are going down, so that would be negative infinity. Now for the domain. X equals 1 is bad. We know that. We also know that we had a hole at -4. So we'll start on the number line at negative infinity. We'll get to -4. We have to jump over it, get back on the number line, but then we're going to hit 1 and back on it, and we're good to go to the right from there. So infinity. The range, this graph is going up and down forever. We can see it's filling everything here. So negative infinity, infinity. Continuous, well, all of them, if you don't use x equals 4 and x equals 1. Those were, again, our vertical asymptote and our hole. So increasing and decreasing. This time we look at these from left to right, and we realize both of these would be increasing. So this time we can just circle increasing, and it's going to go from negative infinity to 1, and from 1 to infinity. Again, you'll notice there's nothing there about the hole, because a point cannot be increasing or decreasing. This is just overall for the interval. Symmetry, well, you know, you look at it and you say, it's probably got some kind of symmetry, but it's not even or odd, and that's all we care about. doesn't have even or odd symmetry. Not bounded, going up and down forever. We have our range of negative infinity to infinity. Nor did it have any turning points. So we don't have any local extrema. And then the end behavior. Limit as x approaches negative infinity for f of x equals. Limit as x approaches positive infinity for f of x equals. And with this one, we didn't have any horizontal asymptote. So what do? Well, we look to the slant asymptotes. And we can see the slant asymptotes are going to be going down forever as we go to the left and up forever as we go to the right. So with this one, we will have negative infinity to the left and positive infinity to the right. So those slant asymptotes come in handy. They were really, really good asymptotes for our graph. We really were hugging those. And then they also help out a lot when you talk about the end behavior. So now, that finishes up number 9, those monster problems of analysis that our objective was basically to get us to this point where we could do all of this. Okay, so hopefully everything will go well here. The smartboard was having some issues. I think there's just too many people using screencast. Section 2.7 is for Friday, and this one is going to feel like, and the smartboard will like it too, because there's not so much going on. This is algebra. That's what we're doing here. So we're solving equations in one variable, and we want to be able to solve rational equations by multiplying by the LCD, the least common denominator, and eliminate extraneous solutions. Reminder, those are false solutions. And solve rational equations by using substitution and the graphing calculator. So a mixture, but basically what we're trying to say is everything in here is going to be solving those rational equations, which means fractions. We're going to have fractions involved. So solving equations in one variable, solving our rational equations. Rational equations are equations involving rational expressions or fractions. Remember the set of rational numbers? We represented this way back in the first week of school. We said Q is quotient. So every rational equation can be written in the form some polynomial f of x divided by some polynomial g of x. And if f of x and g of x are polynomial functions, no common factors because they're not going to cancel out here, then the zeros of f of x are solutions. Because when we solve, we're finding the zeros. And we can't have a 0 in the denominator because we can't divide by 0. So any zeros that we're going to find are going to come from the numerator. To solve an equation involving fractional expressions, we multiply both sides of the equation by the LCD, least common denominator. Clears the equation of fractions, which usually makes people happy. Doesn't mean we're not going to have a fraction answer at the end, but it just means we're not going to work with fractions all the way through. And now, like it says, sometimes the LCD will contain variables. So here's our first one. Example 1 says solving by clearing the fractions. And we see that we have x plus 3 over x equals 4. First thing to do, write them all or think of them all as fractions, so we'd put x over 1 and 4 over 1, and then we find the LCD. Good idea to write it down, and what we have to do is say, all right, I need everything to its highest power, and I need to make sure that I have numbers and variables and binomials and all of those good things that I need. But when I look at this one, I realize the LCD is just going to be x, because the LCD for the numbers is 1, and x is the only variable that I have. So if I multiply everything in this equation by x, I will eliminate my fractions. And that's what I want to do. Most people don't want to work with fractions all the way through. You don't have to. So this will become x squared plus 3, because these x's will cancel out, equals 4x. So now I take a look at it and think, that's a quadratic. and it has a middle term of 4x. I better see what this looks like on one side, so I subtract the 4x. And these, we always factor. If it's at all possible, we factor. So, there's no greatest common monomial factor. It is not a perfect square anything, but having it equal 0 is huge. Make sure you write down equals 0. That's huge. That means that you understand finding the solution is finding the zeros. Two numbers that multiply to 3 and add to negative 4, x minus 3 and x minus 1. We get two solutions, 3 and 1. But there was a warning. That warning was some of these solutions might be extraneous. So we have two ways to check this. The first way would be, hey, let's just plug those back into the original equation. I'm going to touch the blue. Oh, good. Okay, come on, smartboard, help me out here. 3 plus 3 over 3 equals 4. 3 plus 1 equals 4. Beautiful. That one works. Let's try the 1. 1 plus 3 over 1 equals 4. Well, sure it does. Now, what's the other way to check it? With your graphing calculator, where you say one side is y sub 1 and the other side is y sub 2, and you see where they hit each other. Or you move it all over to one side and you find the 0. So we have a lot of ways that we can check these, and it's just a matter of time. You know, how much time you have to check it. The algebra sometimes goes really fast if you have a nice, easy rational equation to look at, but there are other times when you might just want to pop it in the graphing calculator because your answers don't come out pretty. So we're taking a look at solving a rational equation, and again we want to multiply by the LCD, so we realize that our denominator here is a 1 and an x minus 4. So it'll be a 1 and an x minus 4 for our LCD, but why even bother writing down the 1? So we're going to need to multiply this entire equation by x minus 4. Now, every once in a while, that bothers somebody because they're like, well, how can we just multiply across the top of everything and not worry about what's going on with the denominator? Well, don't forget, this is one of our properties of algebra. We can multiply everything in an equation by the same thing, and it will be equivalent. That's the basis of algebra. So we will have x times the quantity x minus 4 plus, here the x minus 4's will cancel out, but we'll still have a 1. Don't lose the 1. And we'll go ahead and distribute. And then we'll take a look because we would just love to factor that. But there's no greatest common monomial factor. It is not a perfect square trinomial because x times 1 doubled is 2x, not 4x. Two numbers that multiply to 1 and add to negative 4? Nope. All right, we're going to complete the square. So move the 1 over. And b over 2 squared will be negative 4 divided by 2 squared. Negative 2 squared is 4. So we will add 4 to both sides. This is now the quantity x minus 2 squared because we made it a perfect square trinomial. That equals 3. We will take the square root of both sides, and x minus 2 equals plus or minus the square root of 3. So adding the 2, we get x equals 2 plus or minus the square root of 3. That's why we couldn't factor it. It had irrational zeros. So now, I do want to show you how you can check these with the graphing calculator, which means we should figure out what 2 plus the square root of 3 is and what 2 minus the square root of 3 is, so that we will know them when we see them. So if you punch that into your calculator, 2 plus the square root of 3 is 3.732, and 2 minus the square root of 3 is going to be 0.268. And that's because the calculator, while it is fabulous, is not going to give us 2 plus the square root of 3 and 2 minus the square root of 3 as our zeros. So what do I put in? Well, you go all the way back up to the beginning. And since it already has a 0 on one side, we want to carefully put x plus 1 over x minus 4 into our calculator. But we're going to need parentheses because we have more than one term in the denominator. So let me get this one out of here. That was example 9. And here it is. So for y sub 2, I have x plus, and then I have that little fraction. The whole thing is in parentheses. 1 divided by parentheses x minus 4, because there are two terms down there. So the calculator knows it's an x, and then there's a fraction. So let's take a look at the graph. Zoom 6, right there. Well, there's two spots where it's crossing, so let's let Blinky help us out with those. Second trace, number 2. Below to the left, above to the right, 0.268. Oh, that's what we had. That was 2 minus the square root of 3. Excellent. We did that one right. Second trace, number 2. Now, for this one, we will be above it. Whoops. To be to the left, enter. Below it, to be to the right, enter. 3.732. Hey, cool. That's 2 plus the square root of 3. So with this one, we would show, we checked this with our graphing calculator, and really the only part that we cared about was that. Right there. The other branch was nice, and you know, it shows us that we're talking about a hyperbolic function, but that was the part that we cared about. We really needed to see those two. All right, so we can use our graphing calculator to check our algebraic solution. We have to check one way or another. So if you really wanted to put these back in, you certainly could do that. The algebra is going to be tougher because we had those irrational zeros in there, but algebraically it works. Just nicer and faster to do it with the graphing calculator. So we are definitely doing what our objective said. We are solving these rational equations by finding that LCD. So extraneous solutions. Well, heads up, we will find extraneous solutions in examples 3 and 4. That happens when you have to raise something to an even power. That is when you are more likely to find extraneous solutions than in any other case. When multiplying or dividing an equation by an expression containing variables, the resulting equation may have solutions that are not solutions of the original equation. And these are extraneous solutions. We did the math right. We got an answer. It should work, and it doesn't. And that's the reality that happens here. For this reason, we must check our solution of the resulting equation back into the original equation to make sure that the solution or solutions we found are a solution at all. All right, so example 3 says eliminating extraneous solutions. They gave us the heads up already. But look at that mess, huh? So what do we want to do? Well, we got to find the LCD, which means we have to have all of our denominators in factored form. So x minus 1 is fine. X minus 3 is fine. But x squared minus 4x plus 3, that needs some factoring. So two numbers that multiply to 3 and add to negative 4, because there's no greatest common monomial factor, and it's not a perfect square trinomial. And it's x minus 1 times x minus 3. Hey, look, that can be our LCD. So we are going to multiply all three of these by the quantity x minus 1 and the quantity x minus 3. And hopefully some good canceling will take place. Here the x minus 1s are gone, and we'll have 2x times the quantity x minus 3. Here the x minus 3's cancel out, and we get 1 times x minus 1, which is just x minus 1. And over here, jackpot, x minus 1s are gone, x minus 3 factors are gone, and we get a 2. So obviously we have some work to do here. We're going to have to distribute and get everything over to one side once we combine our like terms. So 2x squared minus 5x minus 1 equals 2. 2x squared minus 5x minus 3 equals 0. And now, our hope is, please let this be factorable. Now, if you don't want to waste your time and you're thinking, well, I don't want to start factoring here or find the combinations and find out it's not factorable. Remember, you can always stop and do b squared minus 4ac. And if it comes out to be a perfect square, sorry, I had to sneeze. I didn't want to sneeze into my microphone here. That would have been very bad. So b squared minus 4ac, 25 minus 4 times 2 times negative 3. If it comes out to be a perfect square, then it is factorable. So, in this case, like I said, you could do negative 5 squared is 25 minus 4 times 2 times negative 3, 25, and in the back, plus 24. Hey, 49 is a perfect square. We're not going to be wasting our time. This is factorable. So 2x times x obviously is going to give us 2x squared. We just have to figure out, is it negative 1 and positive 3 or positive 1 and negative 3, and where does it need to go? So 2x times negative 3 would give me a negative 6x plus 1 would give me that negative 5x that I need in the middle. So outside times outside is negative 6x, inside times inside is plus 1x, and that gives us our negative 5x. All right, our two zeros here. 2x plus 1 equals 0. We would subtract 1 and divide by 2 and get negative 1/2. And x equals 3. Or does it? So here's the problem. These are quotients. These are fractions. They have denominators. If one of those makes our denominator 0, it's extraneous, and we can't use it. And by golly, look at our LCD. X minus 3. If we put a 3 in there, we're in trouble. 3 is out. It's extraneous. Now, if it doesn't make the denominator equal to 0, that doesn't mean that you went ahead and you did something wrong or right. It just means you got to keep going. You have to check it. So this one, we have an x equaling negative 1/2. And what I did with this one, you could just do it with algebra, but look at this monster that we have up here to begin with. A 2 over x minus 1 plus 1 over x minus 3 equals 2 over, and you'd have to put your negative 1/2 back into there. So I went ahead and just moved it all over to one side and put it in the graphing calculator to show you that it's going to check. So, let me get this one out. And turn this one on. And again, I've got the 2x over x minus 1. All is one fraction. It's in parentheses. Plus 1 all over x minus 3. And the whole thing is in parentheses. And then I subtracted the right-hand side. So subtracted 2 divided by that trinomial x squared minus 4x plus 3. Zoom 6. And I can see it's hitting the x-axis in one spot. So by moving it over, I have a 0 on one side, and let's let Blinky tell us that that's going to be negative 1/2 so that we can verify that it works. And it does. There's negative 0.50. So, with our graphing calculator, we saw that. Graphing calculator, check. X equals negative 1/2. The other solution was extraneous, and that's our false positive. We did the math right. We didn't do anything wrong, but it just doesn't work. And that happens when we start multiplying by x, and we end up getting things that are squared or to the 4th or to the 6th power. It is almost always because we are raising something to an even power that we'll see those zeros created in the denominator. Alrighty, eliminating extraneous solutions. Well, they warned us about that. It was going to happen. So let's go ahead and see those denominators in factored form, because x squared plus 2x pretty obviously is not in factored form. But this is good news. We've got an x and an x plus 2, and that's the highest power for all of that. So if we just multiply everything by our LCD of x and x plus 2, we should have it. So with our first little fraction here, the x's are going to cancel, and we'll get the quantity x plus 2 times the quantity x minus 3. In the second one, our little x plus 2's are going to cancel, and we're going to have 3x. In the third one, jackpot, x's and x plus 1's are gone. And of course, 0 times anything is going to be 0. So let's FOIL these two little binomials together. And we'll have x squared minus x minus 6 plus 3x plus 6 equals 0. Then we'll combine like terms. And we get this. And we realize, superb, because I can factor out that greatest common monomial factor. Again, equals 0, big deal. Make sure you have that equals 0 on there. So our two solutions, x equals 0 and x equals negative 2. We did all the math right, but let's go back and check. Do they work or don't they? Oh my gosh, neither one works. Look at this. This was our LCD. If we put a 0 in there, we'll have a 0 in the denominator. If we put a negative 2 in there, we'll have a 0 in the denominator. Well, what's going on? Neither one of these work. Oh, there's the blue again. I have to quit grabbing that. And we didn't do the math wrong. We did it right. So we'd have to write no solution. So to check this one, you'd want to put it in the graphing calculator with, parentheses upon parentheses. And what you would find is that this is never going to cross the x-axis, which means it doesn't have any solutions. Now, the chances of us putting something like that on a test are pretty doggone low, because we want you to, do the math and actually get something. But every once in a while, putting something on a test that has an extraneous solution, that's going to happen, So you always want to check your solutions when you get done. And that is the first day of section 2.7. So we are just solving our rational equations, I should say. So section 2.7, day 1 is page 232, number 1 through 29, the odds, and 51. So this video finished up that problem number 9 from section 2.6, and then gave you the notes for section 2.7. Happy weekend, everybody.